In chapter 4, and we were looking at these four structures and trying to define their relationships. So we identified that we've got different, identical, and isomers, right? Yes. Yeah. Okay. Within that category, we came up with ways that we could think about and manipulate those to kind of differentiate those relationships. Right? And that's what those definitions are there for. Those definitions, while valid and potentially useful, can get confusing. So oftentimes it's better to organize your flow between those different definitions or separate definitions through a flow chart. Right? And that's what this slide is about. So when we take any two compounds, what we want to do is consider what is their relationship. So the first question we would ask is, do they have the same molecular formula? So if we took a look at these two, do they have the same molecular formula? No, which immediately means that they are different. Sometimes that molecular formula can be challenging because the first thing that we're going to look for are carbons, and the number of carbons, while a big signifier for difference, may not be the answer. You may have to dig into hydrogens. Why does looking at hydrogens become more difficult?
They're implied.
They're implied. You would have to draw them on. Okay? I will still get students all the way through second semester being like, I don't feel like drawing it out because it takes too long. You will screw it up in your head. Okay? The amount of times you screw it up in your head is effectively your threshold. For me personally, the amount of times I screw it up in my head is somewhere in the 50 to 60% range, okay, that I screw it up, okay, which would mean I successfully don't screw it up, 40 to 50% of the time. That's a pretty crappy exam grade, okay? You get to decide where your threshold is. My experience says you are going to screw it up at least as often as I am. I don't want you to have a 40 to 50% on the exam, which means when you see a question, your instinct isn't, how can I figure this out? Your instinct is, I'm drawing this right now. That instinct to draw will save you time, because eventually you're going to need to draw, and if you just drew it from the beginning, there wasn't a delay. If you wait for it, there's a delay. Okay? So draw those pieces out. What if instead of looking at those two, what did I want? I wanted that. Right? I wanted to look at these two. Okay, notice we're already starting to pause. It took a little bit longer. We had to actually count out those pieces. Okay? If we can admit that we can't see that quickly, we could go through and write our carbons on there. How many carbons do we have? 5. Do we have all the right hydrogens? Some very confident no's. Those very confident no's are proof positive that you need to be writing it out. How many hydrogens on that structure? For those people wondering why I'm not saying anything, I'm still trying to draw all of the hydrogens. And we now have 12 and 12. So for the record, you literally just within seconds gave me the direct evidence that you need to write it out. Okay? And not just to me, to you, because you were the ones that said that. Okay? So they have the same molecular formula. So now I move to a new question. Are they superimposable? Okay? That superimposability could be very difficult to see with all the hydrogens, so it might be helpful to delete them all. This is nice. It's nice to have technology. Okay? And we want to go through and try and superimpose these things. Okay? The pattern on superimposability. Let's take a look at those 4 atoms. If I wanted to superimpose, do they superimpose? The red atoms, they do. Okay? Does this blue atom superimpose? Okay, it's definitely not there. Was it just a rotation to get it up to there? No, right? It's actually on the entire other side of the structure. So these are non-superimposable. Right? Because they are non-superimposable, the relationship between them is that they are isomers. Okay? And that's where we ended Monday. We're now going to add an extra step to this and reference the atom connectivity. Okay? This can be kind of a challenging one to differentiate, but it can work if we go through and number. 1, 2, 3, 4, right? 1, 2, 3, 4. So far, so good? Okay. Where is the blue methyl connected in our right structure? Position 4. Where is it connected in our left structure? 2. Do they have the same atom connectivity? No. The numbering is different. Okay? So since it is no, those are now structural isomers. Okay? Stereoisomers at this stage, all you have to be able to do is to identify them. How do you identify them?
They're not structural.
They weren't structural. They weren't different. They weren't just isomers, and they aren't identical. Then they're stereoisomers. Okay. Very quickly, chapter 5, you now have to actually look at stereoisomers because the stereoisomers category subdivides out, okay, into a whole bunch of different sections. Okay. That happens in chapter 5, and that is a very challenging topic to deal with. But before we can get to that, we have to make sure that we can understand the difference between different structural isomers and identical, and that really relies on being able to understand these molecules in 3 dimensions. And when is it just a rotation of a bond versus a physical movement of the atom from one location to another? Okay? That requires understanding our structures, and that's why what we end up doing is looking at model kits. So if we looked at methane, we could look at the model for methane. Okay? We've got 3 representations up there. We have a space filling, okay? We have the ball and stick, and then we also have the Lewis structure. Okay? Each of those are represented equally within the ball and stick model that we can purchase. My recommendation in general, for those people on Monday already heard that, get rid of the hydrogens. Okay? Not get rid of the hydrogens because they aren't useful, they're irritating to pull on and off. Okay? So if I'm on a test and I want to build structures quickly, if I have to remove a bunch of atoms, that takes time. How do I know that's a hydrogen? I'm going to imply it. Okay? I still have the bonds there because I need to show that that space is occupied by something. I now still have methane. Okay? Are there other ways to draw a methane than what are shown up above? Draw what you see. How do we draw that? This is an awesome video, by the way, for recording. Oh, for the love of monkeys. That's why I'm switching. But I'm not switching mid-semester. Right? Is the angry dude holding the model? We've got the carbon. Then what? Okay. 2 dashed lines. Where are the dashed lines? This bond is going away. That bond is going away. What about the bonds out here? Those are wedged coming at you. Is that harder to draw? Yeah, that requires a lot more action. Why would we draw it that way? To show a different orientation of the molecule. That different orientation of the molecule might be more useful to us. It might not. Are you still responsible for knowing that that is still methane? Yes. Okay? So you have to be careful with looking at your molecules to recognize that they can change different directions and shapes and all that kind of fun jazz. And now I have a feeling I'm going to get super irritated. No, I'm not. Cool. Fine. Look at that. If we move up to ethane, C2H6, and we built out a model for that. Ta-da, there's ethane, right? 2 carbons, 6 hydrogens. Notice I have all the hydrogens on there. I don't have to have those on there, but I put them on there. Okay? One of the things that we learned back in our hybridization chapter is that single bonds, the ones connecting the 2 carbons, can freely rotate, right? And single bonds, like the ones connecting the carbon and the hydrogen, can also freely rotate. Did you notice a difference between those? Some people are like, no, those are exactly the same. Do you notice a difference between those rotations? Yes. If you see a difference, what does that mean? You would be drawing something differently. Okay? Does that drawing, is that need to draw something new necessary? Okay? Well, some of that depends on the context. Is it important to draw that? Okay? Well, deciding that has to do with the value of those different drawings. Right? That's where we would sight down that angle. Right? And so if we look at the structure on the left and we sight down that, what would we see? What would I draw? Right? If you're in Monday, stop using fancy words. Okay, what do I see? I've got a carbon, and then what do I have? Well, my drawing only shows 1 carbon. Where's the other carbon? Directly behind it. I can't see it. Okay? I want to, as accurately as possible, represent this molecule. The way I'm going to do that is have to use an inverse perspective. Okay? Because the atom in front is going to block everything. So I'm going to do an inverse perspective, meaning I'm going to make the atom in front really, really, really small. And I'll make the atom in back really, really, really big. Does that make it easier to see? Some people are like, yeah, kind of. Right? Carbons we can imply as points, right? There's a carbon. That's a really small carbon because it's a point. If I move to the back carbon, what's a really large point? A circle. Those hydrogens all overlap each other. That makes it difficult to see them and distinguish them, right? So usually what we do is we do a slight tweak to the structure so that we can actually pick up those hydrogens so that when we draw it, it looks a little bit less messy. Right? That's what we're attempting to do. Right? In that case, each of those bonds overlaps the other bond. Right? Okay? Kind of like how the Earth could overlap the sun when we look at the moon, right? And we would get an eclipse. Did I do that one right? I think I wanted the other one. That's whatever. Phases of the moon. That's what I was talking about. That's why we see the, all those moons. I was thinking of the other one. Okay. In any case, they're eclipsing. They're overlapping each other so that we can't see them. We reference that as an eclipse interaction. Well, what happens if we did a rotation? Because we're allowed to rotate. That doesn't change the energy of that bond, right? Because it's still directly overlapping. Would my drawing change? Yes. So what happens to my drawing? I still get that carbon in front, which I said was black. Let's see, how did I do that? So I kept that one, it looks like. And what happens to the back? Now I have my hydrogen going down, yeah? So I get that interaction. In this case, they aren't eclipsing anymore, right? I can reference them as eclipsing and not eclipsing. I can really call them whatever the hell I want, right? But we're going to add some information to that. What is the accepted language that we use? We call that one eclipsing, and we call that one staggered, because the bonds are staggered away from each other. Okay, is it important to evaluate those? Okay, well, what do each of those lines represent? A bond. What does a bond represent? Electrons. If I take that eclipsing interaction, I have electrons existing in the exact same plane. Right, well, that's not a big deal. Right? Why do we have neutrons? To hold the protons together, because what happens when protons get near each other? They repel. What happens when electrons get near each other? They repel. We don't have the equivalent for neutrons. What we have for electrons is space. They want as much space as possible. This plane now has too many electrons in it, so what do those electrons try to do? Move away from each other. And now we get that staggered conformation. What does that mean to us? Well, that means the staggered conformation is a more stable conformation because it has more space for each of those electrons. If it is more stable, that means lower in energy. We now have a way to look at our drawings to say that's a high energy state versus a low energy state. A large part of what we do to predict reactions has to do with those energetics. Right? That's actually most of what chemistry is about. The job of a chemist is to get things to very high energy states. Why? So that it can react with something else. So that it can relax back down to a lower energy state. Why do I want it to do that? So when it naturally flows downhill, I could insert something in that process so that it siphons the energy out, kind of like a waterfall, a dam, kind of like batteries. That's the whole point, is to look at those different energetics. If we could somehow build something to get it into that high energy state, if we put in a little dam, okay, which we can't do, at least not yet, if we put in a little dam there, this thing is going to naturally want to rotate so that it's staggered. If we put in a dam to resist that, what happens? It starts spinning that dam, and we can get energy out of it because it naturally wants to flow to that lower energy state. Okay? So that's what's happening within these. That observation, while it seems a bit silly and simple, is so valuable that that representation of the model or molecule we name after the person that defined it. And what we've now drawn are Newman projections. Okay? So you are responsible for being able to look at a molecule and evaluate something about its energy. That energy, if you see an energy question, should be a giant red flag that you should be looking at a Newman projection. There are ways that we can overlay information of energetics into other drawings, but ultimately the answer came from looking at the Newman projection correctly. Kind of makes sense? So within our Newman, we now have eclipsed and we have staggered. So far, so good? Okay. So there's our conformations. Okay. As we go up, we might say, well, what happens if we add another carbon? Is that going to change the system? Okay, well, if I add another carbon, I'd have propane. Is that going to change my interactions? I'm still going to get an eclipsed, and I'm still going to get a staggered, right? Is there a difference between that eclipsed versus that eclipsed versus that eclipsed? No, they're all the same. Is there a difference between that staggered, and that staggered? No, notice there were three of them. Why are there three? There's three bonds that could potentially overlap. Okay, so the propane wasn't all that interesting because it didn't change anything. So what do we move up to then? We move up to butane. Right? And for whatever reason, I decided to have the hydrogens on there, so we're sticking with the hydrogens on there. Okay, well, let's look at that Newman projection again. Okay. We got a Newman projection. Is that staggered different from that staggered? Versus that staggered? No, you'll be like, well, then why am I looking at butane? Like, we're just adding carbons and hoping we see something new? Kinda. Are we looking at the right Newman projection? No. The Newman projection is sighting down any bond. So I can look down any bond I want. When we move up to butane, I don't want to sight down the 1,2 bond. I want to sight down the 2,3 bond. So that when I now look down that 2,3 bond and I do the same thing of rotations, am I going to get different staggered energies? Yes. Will I get different eclipsed energies? Yes. That's going to drastically change how I interpret things. If I'm getting different interactions, what do I need? I need new names. Okay? So I now have to define those names for those systems. Okay? Is there a different name for the eclipsed? Yes. Okay? I don't care what it is. Why not? The eclipsed is so high in energy that it is effectively a transition state. And based on your knowledge from 152, what can you tell me about transition states?
Where transition.
It's where it transitions, fair. It's a highest energy, it's a high point. Does anything exist at a high point? No. Okay. So the max value I could really care less about. I need to know that there are different max values, but I don't really care to name them because they aren't really existing at any given instant. What I care about are the low points, because a low point is where the molecule is going to exist for a significant amount of time. Okay? So when we go through and look at our projection, our staggareds, there's a staggered, yes? Sort of, kind of? Okay, some people have models. That's a good idea, particularly for those of you in the Thursday or Wednesday lab, because we're doing models today too. Okay? How about that one? Is that also staggered?
Yes.
Yes. Is it the same staggered? No. Okay, so we have two. Is that staggered? Yes. Is that the same staggered as the last one? How about the one before? Some people are like, no, because it's over here. What is this? A hand. What is this? A hand. They're both hands. Yes, one's on the left, one's on the right, but they're still both hands. Same thing's effectively happening here. The interaction, the energetics are still the same. They're just on different sides. So we only need two new names. Okay? So let's take a look at the bottom one. These groups are as far away from each other as possible. Why would I care about those groups and not, say, the hydrogens? Okay? When we're considering how things interact, we consider size and energetics. What is size? How big something? What is big? If you described me as big, what are you referencing? Be careful. Mass. Okay? I step on the scale. Okay? 215-ish pounds. Okay? Does that make me big? It's an aspect of it, right? Is there another aspect behind it? My height. When we reference big, there's two parts of that. There's big weight, there's big height. Okay? Atoms have the same thing. There's big mass, and then there's big radius, are equivalent of height. Okay? So when we're thinking about how these things are going to interact, what are we referencing when we talk about big? So there's two options. It's either mass or it's radius.
Radius.
Let's look at mass. Where's the mass of this one?
Where?
Yeah, where's the mass of that atom? In the nucleus. Where's the mass of that one? In the nucleus. Okay? Let's envision the size, that radius of that atom is the superdome. ASU's football stadium. Where's the nucleus?
Dead center field.
Okay? How much of dead center field is it occupying?
Marble side.
A marble. Is the mass contributing to an interaction between those two? No. What's interaction? The interaction we're actually looking at. How radius, how tall it is. It's that radius which is dictated by the electron cloud. So we care about the electrons, not the mass. Why would I care about these two carbons versus the hydrogens? Carbon has more electrons than hydrogen. Right? Hydrogen is effectively our 0 point. Anything other than hydrogen has more electrons is going to have a larger size effect than hydrogen. Okay? So if we're looking at this one, those electron clouds are now as far away from each other as humanly possible. Okay? You could say they're on opposite sides of an argument. Okay? So I could be an establishmentarian or I can be an anti-establishmentarian, right? So we could reference that interaction as anti. They're on opposite sides. Anti. What happens if we do a little rotation up there? Are they on opposite sides now? No, in fact, they're on the same side. Okay, so we call them side-sidetarians. Well, that's also same side, isn't it? So that's too vague. I can't do that. Okay? They're kind of close to each other. Okay? Man laws. You walk into the bathroom, which urinal do you use? The one that's not occupied. Good! That's the one that's occupied. You don't do that. That's very high energy. Okay? Most people would frown upon that. Okay? The next person that goes in needs to go as far away as possible. Okay? Because if you use the one right next door, it's a little awkward. What's the French word for awkward? Gauche, gauche, G-A-U-C-H. That interaction there is awkward. That's our Gauche interaction. Okay? Which of those is higher in energy?
Out of which one?
Gauche or anti? See, this is where it becomes tricky. We got a field of different answers coming through this. Okay? High in energy means we're putting a lot of stuff in the same space. Okay? Is the anti high in energy? No, it's actually low in energy. The Gauche is high in energy. Okay? So you have to be careful with highs versus lows. Kind of, sort of? So what we now have are a bunch of different labels. Please reconnect. Thank you. Okay? When we go through and look at our drawings, we had our eclipsed versus our staggered as differentiators. Okay? As soon as we bring in two non-hydrogen things, it changes our interactions. And we'll get the same kind of thing with our eclipsed. But again, I don't care to name those. What I do care to name are the low energy staggered. And in that case, I get this interaction where those two X groups are really close to each other. Okay? The two people peeing next to each other at the urinal. Okay? When you weren't forced to, which also sounds weird, but that's Gauche. Okay? If they're peeing as far away from each other as possible, that's anti. So you need to be able to look at a Newman projection and now predict that. We can now label those. We also know that the anti, as far away from each other as possible, low energy. Close to each other, high energy. Okay? Can we put that all together into one big picture? Because I think it's on the next slide. Assuming I didn't screw it up. Yeah, cool, look at that. Okay. So we're going to start. We're going to look at energy on our y-axis, so up and down. And we're going to look at a rotation around the bond on our x-axis. Okay? This diagram could start in any given rotation set. Okay? But in this case, we're starting it here. High or low energy? High energy. Okay? Peeing in the same urinal. Okay? Without being friends. Okay? Which means friends don't use the same urinal? Yeah, I don't know. Maybe I just had a better childhood than you. High energy, right? How high energy? Really high? Really high. Okay, so where is that? Where's really high on my picture? Really high. Thank you for not pushing that too far. Right? Now we did a rotation. Right? Is that lower in energy or higher in energy? Lower in energy. Right? How low? I don't know. Let's just pick something. Sort of low. Ta-da. Now what happens? I need to avoid the urinal topics anymore. Okay. Is this one lower in energy? Is this one lower in energy?
No.
This is eclipsing. Okay, everybody see that? We're eclipsing bonds again. Okay? Except now, instead of sharing urinals with a guy equal size, you're sharing a urinal with someone smaller in size. It's still awkward. Right? Okay, so that's higher in energy. Is it higher in energy than where we started? No. Okay? So it's higher in energy, but it's probably, like in there. Now what happens when we rotate again? Super low. Okay? And I think someone even said very scientific. I'm going to be a smart ass. We rotate again, or not like I've been smart ass to this whole topic. We did the rotation again. What do we get? Eclipse. That's high in energy. How high in energy?
Not as high as the first one.
Not as high as the first one. How about in comparison to the blue? It's the same, just the other side of it. We do another rotation. Now it's low again, but it's red. We do another rotation. Back to the beginning. Okay? So we're talking about childish things. What have we now done? We just created a diagram. In that diagram, we can now connect the dots. We now have an energy diagram representing the rotation about C2, C3 bond in butane. That's it. That addresses each of those individual aspects. Remember we talked about those high energy states? Those are peaks. Those are transitions. Okay? I can't exist at that point because it's a single point. I'm going to be moving all around it. Okay? I can exist in the well because that's a low point. There could be something that prevents me from going the other direction because it's high both directions. At the peak, there's nothing that prevents me from going either way off because they're both going down. Kind of, sort of? So cool. We now have our energy diagram. Okay? We could go through and actually make it look a lot prettier. Okay? We could go through and put in all those labels on numbers of energies behind those. Kind of like what you did in 152. Did you enjoy that? No, so let's ignore the numbers. As long as you get the relative heights, you're fine. Okay, that's the important part. Do you understand those relative positions? We good?
Yeah.
Cool. So now what happens? Well, now what we do is we check other alkane structures. We now, instead of connecting those carbons one after the other in a chain, we connect them in a circle. Right? And we think about the same idea, the energetics associated with doing that. Okay? And because this is not my model kit, I'm more than happy to do this. If it is your model kit, don't do this. Okay? Cyclopropane, 3 carbons. What do I need to do? It's not mine. I actually don't even know whose it was. It's just up here.
Having trouble there?
There it is. Was that easy? No, why not?
They're very tight. The bonds are full.
Why is that difficult to do? Why is it high in energy? Things are really close, so we can do better than that. What is the bond angle in that triangle? Do better than that. But yes. 60! Freaking trigonometry, geometry, right? You've done that? 60 degrees. Okay? What is it supposed to be? 109.5, because each of those carbons is sp3 hybridized, which means they're tetrahedral. They want 109.5. You're now making them be 60. Is that a good thing? No, they're very unhappy with that. Okay, so there's a ring strain, which I'm probably butchering the names for each of these things, but we've got a ring strain there. Okay, we're talking about energies, which means what should we also be thinking about? What are those? Colorful pictures, do better. Rotations. And that type of drawing was known as a Newman projection. That's where we see energies. What should we be thinking about when we look at our cyclopropane? A Newman projection. So if we sight down one of those bonds, what do you see? Say that again. An eclipsing interaction. There's an eclipsing energy between those bonds that makes it even higher in energy. Right? So the cyclopropane is a very stressed molecule. Okay? It has some weird properties behind it. If you want to talk about that, you can after class, but that's all I really want you to know, is it's a stressed molecule. Okay? So what happens if we go up to butane? Well, we add another carbon. And we make that one, which took arguably a whole lot less time to make because
Less stress.
there's less stress in it, because the angle there is 90. Okay? When it wants to be 109.5. So we're changing the stress of the molecule by adding more carbons in, and it's being allowed to get to a different angle. Okay? It's still energetic, so what do we also need to consider? The Newman projection. And what do we see on the Newman projection? We still get that eclipsing interaction. The butane is the first one that actually does this, because what will happen is it'll actually sacrifice a little bit on the angles inside. Why? Because when it sacrifices a little bit on the inside, what happens to the Newman projection? It becomes slightly less eclipsed. Okay? Don't stress about that, but it does. Okay? What happens if we add another carbon? Even less stressed, until you drop hydrogens. Right? And so there we go. I don't know my trigonometry that well, so I won't ask you for the bond angles in that one. But there we go. We get that. And what happens when, again, we would want to look at the side. And if we look to the side, that looks awfully eclipsed, right? Right? Now look at that. Is it still eclipsed? Now it's staggered. What did I change? We look at it from the side. Is that a flat molecule? No, it naturally puckers a little bit. That one comes up out of the plane. That helps alleviate some of the angle strain, and it alleviates some of that Newman projection eclipsing interaction. Cool. The molecule starts to change its shape on its own. Okay? What shape do we get for a cyclopentane then? Don't tell me a cyclopentagon. Right? We've got 4 atoms roughly in the same plane with one little atom flipped up at the top. It's not a chair. Okay? I could kind of like envision folding this over, like lick the edge and fold it over. I know we don't do that anymore. And you're like, both. I don't lick both either. An envelope. Thank you. We get the envelope formation. Look at your Gmail. It gives you the envelope, and it's got that triangle over the top. That's the thing you would lick and fold down. That's why it's our logo.
Y'all still do that.
Okay. Y'all still do that? Yeah, there you go. Okay. It's the envelope conformation. What happens when we add yet another carbon? Becomes even more stable. As it becomes more stable, again, things start to tweak and change a little bit. Okay? And you'll notice that we get a lot more ability to rotate within that structure. Okay? And as you do those rotations, you should be considering looking at Newman projections. And in this case, when we look at it, what do we see? Eclipse. That's a crap orientation. That's a very high energy orientation. So I might continue to play with it until eventually I happen to accidentally stumble across this conformation, and when I look at it that way, what happened to it? It's not eclipsed anymore, it is fully staggered. Okay? That staggered conformation is now a very stable conformation. It is so stable that I'm now looking at a chair and I want to be like, I want a particular orientation of the carbon atoms in a cyclohexane that I want to be able to associate a name with what that shape is. That shape, as I already gave away, was our chair. It's not super obvious, but it's kind of a recliner. You've got the back on the right-hand side. I've got where I would sit, and then I've got my feet, okay, where I'd hang my feet out over the edge. Okay, and what I've got is that kind of chair. So if I sat in this, I'd be facing that direction. Okay? Or I'd be facing that direction. Or I'd be facing that direction. Or I'd be facing that direction. Okay? So for those people being like, what the hell did you just do? Well, it just looked like you turned your hand. Yeah, that's all I did. There are tons of potential chairs that you can view with an individual molecule. Okay? And that's why representing that chair shape becomes challenging, because depending on the angle you're looking at, you can see different chairs. This is one of the reasons why I build the model. This is one of the reasons why I tell you to build a model. Okay? So that you can see that relationship. So that when you go to draw it, you know what it means. Okay? And that is a difficult concept to get through. Right? But that's what you need to be able to achieve. Okay? The next part is, how would you manipulate it? Okay? Well, each of those manipulations is looking at those rotations and trying to address what things changed within the structure. When we look at this, can you really tell if anything has changed? Someone's like, oh yeah, I totally see that something changed. What changed? Okay, so there you go. You can't tell. That's what silence means. Like, I have no idea what you're talking about, Mike. Okay, that's fair. Okay. Here's a red ball. Let's put something on there so we can see that. There's a chair. If we sat in that chair, where are we facing? That way. Okay. And as I turn, of course, we got to change things a little bit, right? Okay, so now I want to go through that chair flip. So in a chair flip, I'm going to take what used to be the head of the chair, and I now actually want to make that feet. That's where I want to rest my legs. So that, instead of going up, I don't know about you, your feet tend to aim down, unless you broke something, and you aim it down. That was supposed to be a joke. Must have hit too close to home. Now it's down. Now if we sat in that chair, that would be really awkward, right? You'd just be bananaing backwards. So what do you got to do? You take your old feet, move it up. So now which way are you facing? The other direction. Do you see a difference now with that red atom? Yeah, now it's aimed out away from the structure. Whereas in the other case, it's aimed kind of over that structure, right? So we have a difference. So what does that mean? Another name. Okay? We now have to name that difference and acknowledge what it is. Okay? This is where we encounter the ideas of axial and equatorial. So axial, up and down. Equatorial, equator, because it's on kind of the plane-ish of the molecule. Right? Every single carbon has an axial and an equatorial. Some of them are more obvious to see than others. For instance, this red one is now super obvious because it's red and it stands out as different. Right? The other positions will also have axials and equatorials, and they're challenging to see if you don't have them labeled. Right? So we've now identified those positions, right? They were different. But the whole context of this chapter was not just to identify that things were different, it was to identify how they're different in terms of the big E, energy. To determine the energy difference between the equatorial and the axial position, what would I need to do? So someone was like, numbers. We said crap to numbers. But we did talk about, when we're asked for energy, we need to be looking at Newman projections. So you now have to take this three-dimensional object that some of you are like, where? I don't even see a freaking chair. And you now have to orient it so that you see the Newman projection of the chair that you never saw. Okay? And those people are like, this is just stupid. I don't even know what's going on. And you read the textbook, it's going to be the exact same thing. You have to pick up a model kit, and you have to have someone walk you through to show those positions. Okay? Otherwise, you're just guessing in the dark, which is okay, sometimes. There's your Newman projection. Monday's like, totally. I always see that. Wednesday's like, what the hell are you talking about? Okay? It's a bit of a cheat. It's not a Newman projection. It's two. My left and right hand are both Newman projections. What makes chairs more difficult than the butanes? Those two Newman projections are connected to each other through the ring. So all of those anti-eclipse, staggered interactions, gouge, that we talked about with Newman projections, guess what you got to do? Same thing here. And you've got to identify those positions in the chair. Right? There was a, whoa, hand cramp. So massive eye roll in the back. I understand. Okay? But that's what we're trying to do. Okay? So, because we've been looking way too long at the same slide, let's might as well give people something to watch in the video. Okay? Skip that. Cyclopentanes and our cyclohexanes, we're building out those models. We're trying to view those models in ways that make sense. We can look at the side view for our pentane, our cyclopentane, and that's where we got the envelope. Not a big deal. The cyclohexane becomes the big one, and that's what we're looking for, that side view being a chair. Okay? Which means you need to be able to draw a chair. How do you draw a chair? There you go. 4 simple rules. Okay? Color-coded. I need to start with a seat. Okay? When I build a chair, I want to know where I'm sitting first. So I'm going to make 2 staggered, angled, paralleled lines. So staggering them. Okay? Everybody see that? Some people will go through and they'll go like, well, I'm going to do this. They need to be the same length. They're both representing the same carbon-carbon bond, effectively. Different carbon-carbon bond. They're the same length bond. So make sure that your lines are the same length. Okay? Could you angle them the other direction? Yes. You don't have to angle them, what is that, in the positive slope? We could give it a negative slope. Yeah? So we could angle it either way. Okay? Now what do I need to do? Pick the left or right side of the structure. Okay, so I'm roughly cutting this in half. Okay, I'm going to pick the left-hand side. I need to put that just for me. Left-hand side, which line is the shorter line? Top or bottom? The top one. So starting from that top line, I'm going to go up. Why up? Because it's the top line. Okay? Now I can complete out that triangle. Go to the other side. Which line is shorter, top or bottom? The bottom, which means I'm going to go down, complete the triangle. Apparently I got a little shaky hand there. Okay, what happens when it goes to the other side? Same deal. Okay, I'm going to go up, I'm going to go down. I'm going to go down, I'm going to go up. Yeah? What is interesting about these chairs? They're flipped. They're facing opposite directions. If I sit in one chair, I face this way. If I sit in the other chair, I face the opposite direction. Okay? Important landmarks that you should be noting within that drawing. This is where I would put my head. This is where I would put my foot. This is where I would put my head. This is where I would put my head and foot. Okay? This F, okay, if I want to go through a chair flip, remember I said chair flips. Okay, I want to make that foot into a head so it goes upwards, and I'd make my head into a foot so it would go downwards. Yeah? which atom in the right structure is my new head if I did that chair flip? It's that one. Okay? That becomes tricky to deal with. Okay? And what most people end up seeing is they think there's a rotation. There is no rotation, at least not a significant one. When you're going through and being asked to do manipulations of chairs, do the smallest amount of manipulation possible. When you're asked to do a chair flip, 9 times out of 10, what will happen is a student will do a chair flip and a rotation. How do I know? Because I know how to read the diagram. And you end up drawing the wrong structure. Okay? You won't know it's the wrong structure yet because you haven't read chapter 5. Read chapter 5, and now all of a sudden, all of your things, you're like, why was I getting those wrong? Chapter 5 tells you why you're wrong. So you have to be very careful with those manipulations to make sure you're only doing one manipulation at a time. Okay? Kind of, sort of? We'll do some practice here in a second. I want to backtrack on the slides a little bit. Thankfully, there was a little bit of a slide here that reminded me of something. Sisson Trends. So first off, it's a really dumb question because what's the relationship between these structures? They're different. They're different because different amount of carbons. It was a typo. Okay, now what's the difference between them? They have the same molecular formula, so they're not different. Right? Okay. Are they identical? To be identical, they'd have to be superimposable. Could I superimpose them? If I slid that one up on top, yes, that top methyl and that top methyl overlap. What about the bottom methyl? That one's dashed versus wedged. They're aim opposite directions. They don't superimpose, so they're not identical. So that means there could be isomers. Isomers further refines into structural versus stereo. Okay? And that's now deciding on the numerical order versus the spatial order. And that becomes a challenging one to nail down. Okay? In this case, the numerical order is the same. They're both connected. Both methyls are connected to position 1 and 2. The difference is spatially, this CH3 is aimed the opposite direction. Okay? Which means these two are stereoisomers of each other, not structural. Okay? Within that stereoisomer category, you will also encounter things like this. Okay? And the relationship between those two was what? Cis and trans, right? And we talked about it in class. I said, there we go. We've got 2 R groups, you're good. Okay? But what happens if I throw on that? What did I say in class? Can I label that one as cis or trans now? No, I said you couldn't. A little bit of a gray area. Little bit not. Okay. We can differentiate them. We should not be differentiating them with cis and trans because cis and trans is not a naming system. Just because it's not a naming system doesn't mean that people don't use it as one. Okay? And so that's where we have to be a little bit careful. Okay? The rule to differentiate now in using it as a pseudo-naming system is you have to be able to understand something of priorities. We didn't address priorities at that point, so I was trying to just pass it off and not worry about it. And then SmartWork came back and kicked me in the nuts. Okay? So we got to address a little bit on priorities. When assigning priorities for cis and trans, what we are doing is we're cutting that alkene in half, or for that matter, a cyclic structure. The cyclic structure I can't cut in half easily because the half that I'm cutting it in is the plane of the paper, so I can't draw that one. Okay? But with the alkene, I'm cutting it in half, and now I go through and look at each half and assign priorities. The priorities I'm assigning are to the atoms connected. So in this case, it is carbon versus oxygen. Is there a difference? Yes. So since there's a difference, we have to assign a priority. The rule for priority, because it's a rule, someone just created it, don't blame me, is atomic mass. Which has a larger atomic mass? Oxygen. So I'm going to star that because that's the higher priority. I'm going to go to the other half of the molecule and I'm going to do the same thing. What are the two atoms I'm comparing priority for? Carbon and hydrogen. Which has a higher atomic mass? Carbon. Now that I've assigned priorities, now I can split the molecule through the double bond and be like Sisson Trends. Are the stars on the same side or opposite side? Opposite side, so trans. Okay? These rules, thankfully, are also used in assigning R and S, which we'll encounter in the next unit. We're not doing that in this unit. Okay? But it's the same rule set. Okay? So when it comes to the Sisson Trends, as far as your exam goes, I will keep it really, really, really simple. Okay?
Would you label them as E and C? Because that's what I do.
We're not touching E and Z yet. That's the official nomenclature system. We haven't talked about it, so I'm not talking about it. Okay? We can do the same thing with our ring structures. Okay? And we'll address why we can do the same thing with our ring structures here in a second. Okay? When I do cutting that in the plane, I'm now going through and addressing each half first. So each half being hydrogen versus carbon. Which has the higher priority? Carbon. Now I go to the other half. Carbon versus hydrogen. Carbon. Okay. Now where are those? They're on opposite sides. One being down, one being up, which makes that one trans. The top one, cis. Kind of, sort of?
Because it's a single bond, it's not able to rotate, right? But because it's in
Let's try it. Say that again. Because it's a single bond, it's not allowed to rotate?
Because it's in a cyclic...
Single bonds can absolutely rotate. Okay, and I'm going to throw in a couple things here. And I know where you're going. You're right. Don't use single anymore. Single's dumb. It's not single, it's sigma. Okay? Sigma bonds can rotate. Okay? Aren't those all sigma bonds? Why can't it rotate?
Because it's in a cyclic...
The cyclic structure prevented the rotation. Okay? And it prevents the rotation in most cyclic structures. If you add in enough carbons, now it will be able to rotate. How many carbons do you need? You got a model kit, figure it out. Okay? Why is the alkene and the rings both doing the same kind of naming system if they have different bonding? The whole point was talking about the rotation. Let's count backwards. What are possible rings that I could form? So cyclohexane, pentane, butane, propane, ethane. You can't have a cyclic two-carbon structure. That doesn't make any sense at all, right? Like, how would I draw that? I have a carbon here, a carbon here. How would that possibly be cyclic? Oh, I did it. It's called a double bond. That's why our double bonds and our rings have the same nomenclature system as far as cis and trans. A pi bond, a double bond, is effectively a cyclic structure. Okay? It's a bit silly to call it cyclic because there's only 2 points. Okay? But that's why that nomenclature system comes back in. How are we doing? Should we really dig into the crappy one again? Back to the chairs? You got a minute? Okay. So we would need to look at Newman projections. We said there's 2 Newman projections. So we could cite down a C1, C2 bond and a C5, C4 bond. So if you took your ring, there's our model kit. Where's position 1? Where the red atom is, C1. So I want to sight down the C1, C2. What am I looking at right there? Hey, there's a Newman projection. Okay? Someone was adventurous and said eclipsed. Are those bonds eclipsing? Are they in the same plane? No, they're not eclipsed. They are staggered. Okay, so there's one Newman projection. It then says C5, C4. Count it out. 1, 2, 3, 4, 5. There's the other Newman projection.
That would be so. This is a recurring discussion.
So that's what I'm doing when I'm looking at my Newman projection. So what I'm trying to do is sight down that structure. Okay? So if we take our ring structure from the side, right? I was hoping the shadow would work. Okay, I'll move up. There's our chair, right? Everybody see it? Set facing that way. So now what we're doing is we're taking that and we're turning it just a little bit so you can pick up the Newman projection. Okay, you're sighting down. That's the point of the eyeballs. You're sighting down those bonds. Okay? So that's our Newman projection. How is that going to be important for us? Okay, well, next thing it asks is a chair flip. So if I chair flip this, okay, well, where was I sitting when I sat in this? If I sat in it, I'd be facing you, right? Okay, I like it. This is always a fun chapter. You see everybody go. So we're sitting facing you. I need to do a chair flip. So I'm going to take the head and I'm going to do what to it? Pull it down. Take the feet, pull it up. This is why I don't like this model kit. You still see the Newman projection? Okay, some people are like, yeah. Okay? That's our Newman projection. Okay? Has something changed about it? When we take a look at this one, look at those atoms in front, right? Line, line, line. Everybody see that? Okay, what does that look like to you? Right? What's that shape? Except a bunch of different things. Mercedes sign. Okay, there's somebody that clearly has more money than me. Okay. An upside down Y, right? Okay, or a peace sign, right? Was that peace? Peace. Well, okay. So never mind. Let's stick with the Mercedes sign. Now, what happens when we look at the ring flip? What happened to that front carbon? Those bonds. Oh, it changed. Right now, it's to the peace symbol. The peace symbol is the one with that. You don't know? Oh, okay. Clearly not a pacifist, I guess. Okay. There we go. We got a Y shape. Everybody kind of see that? So when we go through the chair flip, the ring changes a little bit. Okay. Not only does it change, if I now sat in it, where would I be facing? Now I'm facing towards me. Okay. We've changed it. So when you're asked to do a ring flip, a chair flip, that's what you're doing. You're rotating bonds. Okay? How do you know you rotated? Was this red aimed up? No, it was out to the side. How would it go from out to the side to up there? I had to rotate what? A bond. What bond? A sigma bond. Okay? And people are like, it's that particular bond. It's every single sigma bond in the cyclohexane. Okay? That's why it's a little bit of a struggle to get the chair flip to go through and happen. Okay? So again, we now want to think about this as a Newman projection. Now that we're here it is. There's that thing. Okay? Do I care about the other Newman projection? Okay? So some people might say yes, some people might say no. Okay? For those people saying no, why do you want to say no? Because you're confused. Okay, fair enough. What are the atoms? They're just hydrogens. Hydrogens is our 0 point, our baseline. Who cares? So I don't care. Those people saying yes might say why? Is it only hydrogens that are connected? There's carbons. There's these two carbons. The carbons of the ring are part of that. What is that interaction? Okay? We turn it a little bit. What is that interaction? That looks kind of like they're kind of standing close to each other, right? They're a little bit awkward. They're gauche, whatever it is. Okay? As you go through your chair flips, you'll find that you will never get rid of that gauche interaction. Okay? It's either gauche with the ring itself is gauche with itself, or it is eclipsed. So there is no way to get rid of that interaction. If there's no way to get rid of it, guess what? It's a zero. We can ignore it. So we're going to focus now on the other side, that red atom. What is that red atom interacting with? What carbon? Okay, I heard a carbon 6. Carbon 6 is right here, based off of how we counted. Yes, it is interacting with that. Is that interaction ever going to change?
No.
Why not? They're both bonded to the exact same carbon. No matter what way you rotate this, that angle is never going to change. That's the tetrahedral shape. What is it close to if not 6? 3. There's that 3 interaction. If we look at where my hand and the pen are pointing, what kind of interaction is that? That is gauche. This was not a good day to do shoulders, for the record. Oh. That is a gauche interaction. So that red atom that was aimed up and down, which made it axial, has a gauche interaction with the ring. Is gauche good?
No.
Better than eclipsed. Okay? Is it the best? No. So let's say it's crap. It's bad. I want to go away from that. Could it rotate in this way? No. Why not?
Less space.
Less space and I'm breaking the molecule. That's why I can't rotate that way. So where does it need to rotate? It needs to rotate the other way. Now where would it be? It would be on the equator. It would be equatorial. Let's go back to that same Newman projection. We're referencing that carbon in front, right? What is that interaction? Is that still gauche? It is now anti. Which one was more stable? Anti. Which direction do I want my large group to be? I want it to be equatorial because the equatorial generates the lower energy interaction with the ring. Anti is more stable than gauche. Okay? Let's drop that one again. Equatorial, more stable than axial. Do I need to draw a Newman projection anymore? Nope. I now have my answer. When I draw a chair, I want my big group to be equatorial. Right? Why? Newman projections. You don't like the Newman projections? You can mostly forget about them and just remember equatorial is more stable. Ta-da! Right? Just because we got to be a jerk, always, right? We said it had that anti-interaction. Is that it? Right? So just to be extra particular, this was the one we were looking at, right? That had the anti, that carbon, that color on it, right? Is it anti with that anymore? Wait, what? It's eclipsed.
I don't know.
Whoa. Oh. My hand just like massively cramped up.
Yeah.
So, is that orange or is that black atom in the Newman projection anymore? No. So I can't reference it. Oh.
Today is not your day.
Oh. Is it anti to anything? Oh, I don't think I can hold this anymore. Is it anti to anything?
Yes. The first grade.
Are you okay?
My hand is, I can't actually close my hand. It's cramping really badly. Is it anti to that atom anymore? Look. Do you see this Newman projection?
Yes.
What is it anti to? Is it anti to another carbon atom?
Yes.
What is my finger holding on to?
Carbon.
A carbon that is anti to the red atom. How many Newman projections do you have to evaluate to see all your energetics? Not a lot. 2. 2, because off of that carbon, how many carbon-carbon bonds could you cite down? 2. So when asked for how many Gauss interactions there are, how many anti-interactions, you have to recognize that you have 2 bonds that you should be thinking about when you're evaluating those interactions. Okay? That is not a common question from me. It is a question in the smart work because I want you to recognize the model is 3-dimensional. There are 2 different directions you can look at it. That is a challenging question to deal with. Okay? But that's where that's coming from. Okay? Oh. Jeez. Okay. So, if we look at the 2 positions again, we've got our equatorial labeled in red and our axial labeled in blue. If I go through and sat in this chair, where would I be facing? You're like, I don't even see a friggin' chair. I know. Breathe. Look carefully. We'd be facing through the board. Okay? Through the board because this carbon is where I would have my head. This carbon would be my feet. So if I went through and did a chair flip, what happens? That head gets pulled down, that feet gets pulled up. What happened to that equatorial position when I did that chair flip? What was equatorial became axial. What do you think is going to happen here? The exact same thing. Okay? So that when we go through and flip, that red atom now becomes axial. That was our former equatorial. The blue atom is now equatorial. That was our former axial. So every time you do a chair flip, you will change your atom from being axial to equatorial, okay, or equatorial to axial. Which means when you're given an overhead view on a structure, how do you know the most stable conformation of it? Okay, it has to be drawn equatorial. Did I draw that equatorial?
Yes.
It's a trick question. The overhead view has none of that information. Okay? But it's aimed up. You're right. The axial here is aimed up totally, isn't it? Yeah? Everybody see that? It's aimed up. Where's this equatorial aimed?
Up as well.
It's also aimed up. Okay? The overhead view does not address energies. Officially, neither does the chair. The chair we've overlaid information on saying equatorial is more stable because we looked at the Newman projection to see that stability. Okay? So be aware of those stages when you cycle through those. Okay? There's some examples here. Really, I want to look and see what we've got left. Hayworth projection, I'm not going to test on, at least not this section. I just want you to be familiar with it. That Hayworth is taking effectively your ring and turning it on its side, but not as a chair. Why not? Guess who invented Hayworth projections? Biologists. They can't understand chairs. Okay. Where does it really show up? Does that look familiar to you? Those are carbohydrates. Why do we draw out our carbohydrates in Hayworth projections and not chairs?
Biologists are dumb.
Nah, that's a bit overstated. because it would really suck to have to draw multiple chairs out like that, right? Okay. So there is a reason behind it. It's just we typically don't see that because the structures we look at are much simpler than what they would look at in biology. Okay. So there are some sections within chapter 4 that you should just kind of look at. I'm not going to talk about them in any detail, at least this unit. That formula is going to show up in the next unit. Chapter 5. Okay, I know we're done, so if you've got to run, you've got to run. But we have one more lecture. Okay, and what I'm trying to do is get an idea of how far into chapter 5 I want to go. Officially, we have a whole nother freaking lecture that can go on to the test. If we don't put it on the test, what happens on Monday? You don't listen to anything I say. Okay, so it's going to be on the test. The question is, how much do we put on there? Okay. Definition of chirality, I think, is fair game. That was our simple classification. What we really need to be getting to
No way.
is that. Okay. So that isn't a whole lot more slides. And for those people going, oh my God, look at all that crap up there. You know most of it. All of that you already knew. Okay? All you're adding on are those last things. Okay? So we'll look at kind of simple applications for how to identify chiral atoms, because that's the big swinger on this. Okay? On Monday, that's what those previous slides were addressing. Then it's really just kind of practice with it. Limited questions because we haven't gone over it a whole lot. Okay? To my knowledge, as far as chapter 5 goes, I don't know the sections on it, but when you start seeing something about optical activity, stop. Don't read that. Everything before optical activity is addressing those extra definitions and how to kind of see them. Okay? So the textbook's going to provide some ways that you can visualize it. 95% of it is visualization. If you can't visualize, it doesn't matter if I talk about it or not. Get a model kit. Okay? To give you an idea on why that's so important, what I'll end with, come on, where's that slide? Those two structures at the top, find out their relationship.